very honoured to be able to talk here at the birthplace of toposes. In light of all the excellent talks, I feel my offering may be slightly more humble, but hopefully the conjunction of some ideas existing and a couple of new ones will be interesting to some people, and they might feel like looking into this further. Okay, so I have some terminology and a disclaimer. There was references to universes and so forth earlier in the week. If you like, take two universes. U inside V, things in U will be small, things in V will be moderate. Anything not in U will be large, anything not in V will be very large. I won't refer to this again because it's in the background and sometimes you can dispense with this totally, but if it makes you feel more comfortable, take it. Also, unless I say otherwise, all toposes, and I'm dealing with elementary toposes a lot, so I'll get into that in a bit. All toposes co-complete with natural number object, but I don't want to say, take a co-complete elementary topos with a natural number object over and over again. Okay, some disclaimers. Terminology. So here's some terminology which is sort of not, maybe 4 or 5 years old, but not widely circulated. So it's helpful to keep in mind, especially when talking about the relation between sort of forcing techniques, which are coming from set theory, in particular ZFC set theory, and set theory not using ZFC. So material sets, this is where elements of sets have independent material existence. So the elements of a set in ZFC, say, C is optional, or bounded Zermelo set theory with choice, optional again. Those who know the history of this area, this one turns up a lot when talking about topos theory. These are material sets. Their elements are sets too, which are objects of the theory. Structural sets is where everything is, there's no good technical definition, but it's roughly where everything is invariant under isomorphism. You don't worry where you say, take the reals, and then you have to think, do I mean the power set of the natural numbers, the functions from the natural numbers for the natural numbers, the set of all Dedekind cuts such that blah, 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 blah. It's just the real numbers. It is what it is, they're all isomorphic. I don't have to worry about the elements accidentally coinciding with elements of another set. So structural sets, of course, Laviere's elementary theory of the category of sets, the primordial example, maybe some variants on this, and one that I'd like to advertise called Sets, Elements, and Relations, or SEER, due to Mike Schurman, whose name we've heard a couple of times already. And this is not published, but it's on the NLab. Yes, thank you. It is a structural set theory that is not a categorical set theory. So you often hear people talking categorical set theory versus whatever, ZFC. It's a structural set theory where the axioms are purely on sets, how they behave, elements, how they behave, relations, how they behave. 3 sorted, it's about 4 axioms, so shorter than the ETCS list. And after like 2.5 axioms, you've got yourself most of a topos. It's really quick. So yes, material sets and structural sets. All right. So let's do some history. Yes.
So I've heard that ETCS is slightly weaker than Zermelo.
Yes, it's the same strength as bounded Zermelo with choice, but this paper that Ingo mentioned in his talk, Stack Semantics and Structural Comparison of Material and Structural Set Theories, it gives a formulation in this extended internal language, which recovers full ZFC. There's a property called autology, and when you can show that formulas are actually classified by sub-objects and so forth. It's very nice. So I can say structural set theory and recover full ZFC strength. There's no issue with this. There are other people too, like McClarty and others, who have come up with replacement axiom analogs for ETCS. Okay, so a bit of history. But in an ahistorical sense. So consider the topos of sets, and then consider the subcategory of injections, and then the pre-order, the partial order reflection of this is the category of cardinals and the usual order relation, the strict order relation here. So this is, there you go, cardinals, easy. Half of Georg Cantor's life in one line. So important thing to note is that the power set restricts to sets and injections, because the power set of a subset is a subset of the power of the set of the superset. And with the universal property here, this restricts. I'm going to call this on this side. So everything here is classical. We'll get to some more general topos stuff later. And this here is the continuum function. Of course, the continuum hypothesis was, what value does this take when you plug in the natural numbers? Is there sort of some A and these are strict inequalities here. So as we all know, Gödel construct a model of ZFC where there is no such A. Any such A that's in between here with potentially equality, it's either the natural numbers or its power set. And then Cohen came along and gave us forcing, and he said, well, I can construct a set A, construct a new set of a new model of set theory, and I build it explicitly with a set A in here, with these two different. It's a very nice write-up of this in Moerdijk and McLean's book from category theoretic point of view. But they have some nice historical comments and so forth. And they say you can actually see the shadow of the topos theoretic argument in Cohen's paper. I'll get to that in just a moment. Of course, there's a more general question. This is a partial, or a class size partial order, and you have an endo function. What can this endo function do? Given that we can find different categories of sets where it may exclude, it may miss values. What can it do? So there's two cases. So let's say behavior. There's two cases. The regular case. So these are technical conditions, singular case. So these are conditions on cardinals. The regulars are the nice ones, like the natural numbers are regular, assuming choice, things like the real numbers have a regular cardinality. Singular things is like Aleph sub omega, if that means anything to you. Singular cardinals are sort of weird. This is hard and open. This is solved by Easton.
What is solved?
We know exactly what the behavior of the continuum function is on regular cardinals, in the sense that we can characterize precisely what behavior it can have, what it can't do, etc. And so, yes, and people like Scheller write literally hundreds of papers. I mean, Scheller himself literally writes hundreds of papers on this, but other people write hundreds of papers generally, trying to attack this problem for the singular cardinals hypothesis and so on. So why is P so important? This is a set theory notion. Why do we care about it as topos theorists? So here's a definition of an elementary topos, because I don't believe we've had one. Well, I think one was given in Ben Abu's lecture. he wasn't happy with it. Here's one I'm sure some people may like. Finite limits, power objects. And we know a topos has incredibly rich internal logic. You can do all sorts of things, co-limits, limits, descent of certain things. Finite limits is pretty weak. Everything else comes from the power objects. In fact, you can relax this even further, but then you're starting to get silly. So this is saying, for all objects x, I have another object px, a relation from x to px, such that any other object y, a relation from x to y, there's a unique map f, and such that this square is a pullback. So this is just, all the magic happens from this. It's just incredible. So looking at the behavior of the power object functor, or the power set functor in the set theory case, somehow it has incredible freedom, as we see from the set theory, but in fact it gives us lots of structure. So it's good to sort of understand what's going on here. I mean, this is solved purely in classical logic with choice. If you throw away choice, set theorists run screaming from the room and say, I don't know what cofinality is. It doesn't make sense. Why do you want to do it? I don't know, maybe. So there's, all right. So forcing, I'm going to talk about forcing. So forcing is sheaves. This is full stop. There's nothing mysterious about it. Details perhaps, but here's the cartoon I like to draw. Traditionally, start with ZFC, start with a small partial order, and it's a site with a double negation topology. Take sheaves on it, ignoring that. All right, now you have two options here. You can take internal logic, and then you just reason in that. It's perfectly good. And then you perform a construction due variously to Cole, Mitchell, Osius, Foreman, and Hayashi, various facets of it. And then you get what the set theorists call a Boolean valued model of ZFC. And the Boolean is the thing is, this is a topology on this partial order. Take the Boolean algebra of regular opens, and then this Boolean algebra is where your truth values lie. And another way to do it is go further, take, let's see.
So then P is what, any poset?
Partial order with top, poset. It's without loss of generality, assume it's got a top element, but that's, yes, any small poset.
And what is this double negation sign for a poset?
Oh, this is so this is the site. This is a small site, double negation topology. Sieves are downward closed dense sets. So there's an analog of this topology for an arbitrary category. It's called the dense topology. It corresponds to the double negation topology when you pass to the pre-sheaves on that category in the sort of Leviatiani topology sense.
So it is a sieve on P built in a category.
So yeah, partial order, think of it as a category where like this. And you have a top element, and you think of it as being going down. And the further down you go, it tells you more and more partial information about the things you get in here. Okay, so that's one thing to do. You wanted this. Or you take, in your category of sets, the external subobjects of the of the terminal object, and you take a filter. So this is a bit like a point, but not quite, because you require different things on this phi. And you can perform what's called the filter quotient construction. The details are not important, but this here is now well pointed. The internal logic and the external logic now agree in this category. And so you can reason exactly as if you were in the internal logic, but you just go, well, this is how the objects of this topos works. And then you perform this construction again, visual these various people, and then you get, the forced model. So set theorists will sort of flick back and forwards between these two viewpoints as convenient. Now the thing is, these dotted lines, this is a rather delicate and complicated construction involving transfinite, well-ordered, rooted trees. Set theorists don't like it if you say that set theory is a study of well-founded, pointed trees, but it's not really, but that's what they're studying. So, so this is the step that we like. And perhaps just tack on the internal logic, because that's where all the action happens. Yeah, and if you read Cohen's paper, you can see he's describing, exactly these constructions in some sort of sense, as Murdoch and McLean mentioned. There are all sorts of variants. You can consider a topological group acting by automorphisms on my partial order, and then consider equivariant sheaves. This is called symmetric sub-models. You just take a topological group, full stop, and consider continuous actions of this. This is what are called permutation models. And they don't give you models of ZFC, but with atoms. So this predated Cohen by about 40 years, and it's basically forcing, but set theorists are like, that's not real set theory, atoms. So, but it fits into the category theoretic picture perfectly well. Okay, now here's the important point. Taking a poset, we can only affect set many continuum, the values of the continuum function. If we start with a model of set theory, look at the continuum function, do some forcing, the continuum function changes. But this procedure with a poset can only affect set many. It's a particular bound above based on the cardinality of P. But the problem is Easton's solution involved adjusting a proper class of the continuum function at a proper class of regular cardinals. So you can't sort of go, literally, you can take all the regular cardinals, of which there are, I can't say most of the universe, but it just keeps going up. He was able to shift them, subject to the hypotheses of his theorem.
Yeah, so set many means not the cardinality of all sets many. It means
No. That means a set. There's a set, and that is the cardinality of the number of values of the continuum function which you have altered. So you can't affect arbitrarily high values of the continuum function by taking sheaves on a small partial order. Okay, and what he did, he genuinely did it. He adjusted a proper class of values of the continuum function one at a time. This might make you pause. I have discussions with Urs.
Okay.
Pardon?
Questions?
Now?
Can you continue?
Yes, please. Yes. Okay, speed it up. All right. So there's two notions from SGA which I found which are very beautiful. So this notion of four topos. This is for Grothendieck and Verdier and so on. This is because they were thinking Grothendieck toposes. And so for us, this is an unbounded set topos. So this is a topos with a geometric morphism to set. But E is not a Grothendieck topos. In particular, so the example they give is you take a large pro group and then you consider, so again, universes as needed. You take the limit of this pro group and then you consider continuous actions of this. And this is, up to some small care as to what you mean. This is a perfectly good locally small category, which is a topos with a geometric morphism to set. And, it is perfectly good topos. And moreover, if you write down naively a site of definition for this, it is indeed a large site. I have an application of this in paper in Studia Logica early this year. Actually, it's quite nice. And it uses this unbounded quantifier as internal logic. This is too restrictive. This is not what Easton used. Consider, let's see, filtered and well-founded category, initial object. You can consider a diagram of sites, and I'd like to advertise the morphisms which are fibrations of sites due to Moerdijk. You can take sheaves, you go to topos with bounded morphisms, and this is an example, well, it gives rise to an example of a fibered topos, also in SGA4, and they consider the case where R is small, and you can take the total topos or the lax, in my case, probably the pseudo limit of this, and they get a topos, and people have apparently applied this in algebraic geometry. But if R is large, you just can't do it. If you forget to in fact, you probably want.
So what is the hypothesis here?
Sorry, bounded. These are Grothendieck toposes. This is sheaves. So this morphisms of sites. So this is probably what you'd call a morphism of sites in the sort of Grothendieck style, but in fact this is just the right adjoint to a fibration. And this notion, if you think of sites as like a basis for a topos in this sort of sense we've heard today, a fibration of sites is almost exactly analogous to Jordan normal form. It's not true. You can pick C, pick a basis for one of your toposes, and then you pick an internal site of definition for the topos sitting over the sheaves on this, and then you can pull this down and you get a very nice expression. We have these adjoint functors with cover preserving properties. You can characterize, it's extending this site characterization to characterizations of geometric morphisms by these particular fibrations. Moerdijk covers a bunch of examples of these. It's just, I think it should be advertised more widely given this sort of viewpoint of sort of using a basis. Okay, so get back to here.
What is a CC?
Co-continuous lex, and this is now a very large category. So I'm thinking of toposes. I have sites and then sheaves over them sit on here. Lex is sort of starting to creep up. Just one more universe.
So what is the two category then?
This is so this
normally means left exact, but if you are talking about co-continuous, then you have co-limits probably as well.
Yes, because Grothendieck toposes are co-complete, and I'm taking the inverse image functors here, and I take the two arrows which make the conventions work. And we've seen there are different conventions. You pick the one that works.
Yeah.
So what is the lex? What is lex?
Finite limits, co-limits, I mean, it's what you might call a presentable category, but minus the actual presentability. Because these are, they factor through presentable, this sort of algebraic notion. But I want to go to the lex, because what happens next is I take, so let's call this big diagram E, and I let E star be opposite. So R to lex CC. R is a filtered, well-founded category with, think of it as the ordinals. With, initial object. Initial object, not a zero object.
Initial object. And
Yes.
then you have a map from this to sites with vibrations
Yeah.
as morphisms.
Yeah, and then you can take toposes, and then you just take inverse images, the inverse image part. These are like the algebraic viewpoint on toposes. I'm forgetting the direct image functors, because the direct image functors will no longer exist in the next step. And I take the colimit over R of E star from R. Now, this is not a locally small category in general, but you have some universes, or you take the first order theory of categories, and this is what Easton does. He picks an appropriate R. In fact, it's just a class of regular cardinals. Defines appropriate sites, which affect one value of the continuum function at a time, and then he takes a colimit. It's affecting all the regular cardinals sitting in my diagram category.
That's a two-categorical colimit?
Yes, pseudo. So sometimes I call this the Easton. It's not a topos a priori. So got to say the theorem. So, he has very specific choices, yes? Is that a quick? Oh no, you just don't. Okay. So E is, it's almost a topos. Co-complete, heighting pre-topos with finitary W types, e.g. a natural number object. So this is, the internal logic here is first order intuitionistic logic. You get heighting algebras as your subobject lattices. W types means it has algebras for, initial algebras for polynomial functors associated to maps, which are numerals in a slice category. So very, literally a finite polynomial. Natural numbers are an example of this. And if, so notation is above, so for every indexing object, every topos, every object in it, say power set of X is eventually constant, and you can formulate this in just a straightforward technical sense. It means as you keep going by your inverse image functors, eventually the power object stabilizes, and then there's isomorphisms all the way up. It doesn't change.
Very.
Hey?
It's a very phenomenon.
A what phenomenon?
Never mind.
If this is true, then E is a topos. This is exactly the condition that Easton finds, and he characterizes the special case of fibration of sites that he's using that makes this work. And he's doing localic toposes, so all he needs is not for every object in the indexing category, but just in the base category. So for every set in my base category, if its power set eventually stabilizes after passing by the inverse image functors after this class-long diagram, then he gets a topos. So you get power. So adding power objects. So all you miss are this.
So the sequence of the power objects of the representables has to stabilize. Or-
Yes. Yes. Exactly. And in fact, you don't need all of them. You can just take some cofinite sort of collection inside the order of cardinals. You know, for large enough, you don't need to check all of them. You just need an unbounded sequence of cardinals. So here we don't have internal. You don't have internal HOMs, but adding your power set, you get all the topos theoretic structures. But I think I'm over time, so I was going to give explain Easton's example of how he characterizes this eventually constant in terms of properties of the posets, but you can see me if you're interested. Thank you very much for your time.
What was can you recall what was the notion of vibration of sight?
Ah, yes, yes. So let me just, so P is a fibration of categories. So, you know, whatever Cartesian lifts, so on. It is left adjoint to a fully faithful functor going in the other direction. And T preserves covers.
You're speaking now about sites or toposes?
These are just sites. These are just sites. So I didn't write the topologies here, but this is the underlying categories, and yeah, there are topologies here and here.
And there are no special assumptions like existence of finite limit or...
No. But without loss of generality, if you have complete freedom, you can actually choose C and D to have finite limits, if you like. But there are important cases when they don't have them, so it works in more generality.
Because the notion of preserving covering sheaves is not as good, so if you don't have...
Yeah, it's like flatness or something or other. Yeah.
Yes, function is not a morphism.
Yeah, the image of a covering sieve generates a sieve and, you know, various things, yeah. So it's in Moerdijk's, it's in the Elephant and Moerdijk's paper from, I should say what year it is to, cite, 1986. So this is a very nice notion, and it's only in his paper and in the Elephant, and the Elephant doesn't elaborate on his paper. So I think it should be pushed more because it's quite a useful technique.
So is the category well powered, the one on the left blackboard that you were hiding right now?
Here?
If you say co-complete hiding grid topos,
No.
you're not okay.
No.
So because I was about to say that the hiding is automatic if you're co-complete, but only if it's...
So it's sort of like small heighting, if you like.
Okay.
Yeah. And it's not even well powered once it becomes a topos, but it has power objects. And it's because of this lack of local smallness that you don't get the adjoint functor theorem to get all the direct image functors that you might think from the cocone of the diagram. So this is something like a limit, except it's really only in the algebraic morphism of topos sense. You can't find the right adjoints.
What is the B? Topos B?
Bounded morphisms.
But for all morphisms, if we use usual Grothendieck toposes?
Yeah. But that's over set. I mean, that's like topos slash set. You know, Grothendieck toposes over set. Then automatically morphisms between them are bounded. But I have to forget set anyway because I no longer have the right adjoint, the global sections functor down to set. So I have to forget that I'm sliced over set.
This is just because of size issues?
Yeah, so I probably have something like up here, instead of like top over set, as you know, arithmetic toposes, I have lex categories under set. And so I have constant sheaves, but in this big topos curly E, but I don't have global sections.
Yes, when you say co-complete pretopos, do you mean what Peter Johnson called infinity pretopos? Or is there a problem with arbitrary?
Oh, yeah, yes, no, sorry, yeah. It's an infinitary pretopos, sorry. So they call it an infinity pretopos, but we have infinity toposes, so yeah, all coproducts, small coproducts.
Yeah, and the co-equalizers you get for free because you have a natural numbers object.
Yeah, you can generate equivalence relations